Hello, my name is Emilian, and I will present the paper Adversarial Permutation Invariant Training for Universal Sound Separation. In the field of sound separation, our objective is to extract the individual sources that constitute a given mixture. A well-known example of this is music source separation, where sources in the training set belong to well-defined classes, such as vocals and guitar. In this work, we focus on the more challenging problem of universal sound separation. Universal sound separation aims to separate any type of sound from a mixture, regardless of its class. In this scenario, we do not have any prior information about the classes of the sources, making the problem significantly more difficult. The standard training technique in supervised universal sound separation is permutation invariance training, and was initially proposed within the speech separation literature. In the illustrated animation, we can observe that the mixture is fed into the separator. The separator then processes the mixture and generates the estimated sources. On the right side, we can see the ground truth sources. Permutation invariant training trains the model using the regressor loss LPIT, which is computed with the best permutation between the estimated sources and the ground truth sources. This approach ensures that the model learns to separate the individual components without any information regarding their true ordering. In our work, we propose the use of adversarial training for universal sound separation. Previous PIT-based adversarial techniques in speech source separation, such as SS-GAN-PIT, have some limitations. These techniques primarily focus on separating only two sources and are limited to speech. However, our goal is to generalize this approach to handle the class-agnostic case with more than two sources. To achieve this, we introduce multi-discriminator training for sound separation and a novel eye replacement context-based discriminator. In our approach, we utilize a mask-based unit separator architecture. We define discriminators at three levels: mask, STFT magnitude spectrogram, and waveform. For each level, we have two types of discriminators: instance-based and context-based. To keep our presentation concise, we will focus on showcasing only the waveform discriminators. Let us describe instance-based discriminators. After estimating the sources from the mixture, instance-based discriminators process a single estimate and compute the fake hinge loss. Then they process a single ground truth signal and calculate the real hinge loss. We repeat this process for all sources and sum up the individual losses to obtain the final discriminator loss. Instance-based discriminators are commonly employed in source separation, and they assess that a single source belongs to a certain class. In our setting, we employ them to assess the realness of an individual sound, not having knowledge of classes. In the following slides, we describe the process of computing the loss of an eye replacement context-based discriminator, which we introduce. First, we separate the mixture using the separator. We then compute the optimal permutation matrix between the estimates and the ground truth sources as in standard PIT. Next, we permute the estimated sources and rename them accordingly. We proceed by creating a copy of the permuted estimations. At this point, we randomly sample a set of eye replacement indices denoted by gamma, with I being inferior to the maximum number of sources. We then replace the estimates indexed in gamma with their corresponding ground truth sources, forming a fake contextual input. The context-based discriminator takes the eye replaced estimated sources, computing the fake hinge loss. Then it inputs the set of ground truth sources, outputting the real hinge loss. By summing these two hinge losses, we obtain the final discriminator loss. Different from instance-based discriminators, context-based discriminators consider the relationship between the separated sources and whether they are consistent with the original mixture. The latter can be fed to the discriminator as an optional input. Our novel replacement strategy avoids a naive solution where the separator bypasses the mixture as an estimated source, makes it more challenging for the discriminator to distinguish between real and fake separations, leading to an improved adversarial loss. And finally, we find out that by training with eye replacement context-based discriminators is sufficient to enforce the separation task. So it is possible to train the separator without the regression loss, maintaining the same quality. For training and evaluating our model, we use the free universal sound separation dataset, which is the standard dataset for supervised universal sound separation. It was used to train the baseline to which we compare, the Google DK's 2020 model, which is the current state of the art on the task. It is composed of 10-second mixes containing up to 4 sources. Our primary evaluation metric is the scale invariant signal-to-noise ratio, SI-SNR, from which we derive two metrics. For mixtures containing more than one source, we calculate the SI-SNR improvement relative to the mixture baseline. For single-source mixtures, we compute the SI-SNR directly, which we refer to as the single SI-SNR or SI-SNRs. We studied the SI-SNRi and the SI-SNRs when training with a single context-based discriminator. We vary the number of replaced sources I, the data type, and whether the discriminator is fed with the mixture or not. We see that without replacement, as in speech adversarial bit, the SI-SNRi matrix is lowest and the SI-SNRs is highest. The model bypasses the mixture into the estimates, producing a bad separation. This finding highlights the importance of replacement for achieving improved metrics in adversarial pit. We train our models with I equals 3, given that it performed better on average on SI-SNRi. In this table, we ablate the usage of discriminators. Just by adding multiple discriminator losses to the regressor loss, which is the waveform logarithmic mean square error, we obtain 1.4 dB SI-SNRi improvement over our pit baseline, without changing the separator architecture or the dataset. With respect to the Google Decades 2020 baseline, we obtain a 1 dB SI-SNRi improvement. Finally, by using multiple context-based discriminators during training, we can achieve the same level of separation quality as we would when training with the regressor loss, without the need to use the regressor loss at all. We conclude the presentation showcasing that spectral holes, ubiquitous to mask-based separators, are reduced by our adversarial training. Let us listen to the third reference source. The decay's baseline estimates sound like this. Our adversarial pit estimate instead sounds like this. Thank you for your attention.